So here we have some PDE, and the chief problem with this is that we have these non-homogeneous boundary conditions. And so the idea is to change to a new dependent variable that's basically going to subtract away these boundary conditions and move them into a source term in the PDE, and maybe also affect the initial conditions. So just to see where the idea comes from, recall that if you're in any vector space, the linear interpolation between 2 points in that vector space. So the linear interpolation of A and B is, and so this is sometimes called the straight line path. So let's see, so if you are at some location A and there's some other location over here, B, and you want to get from A to B like this, then what you need to do is say, okay, I'm going to start at A, and then I'm going to go in the direction of B, and so this vector is B minus A, and I'm going to do that for some amount of time. And so this formula here says start at A and then head toward B for t seconds. And that'll take you from here along this path over to B. And it's also often written as, oh, actually, you know what? Sorry. Let me change the variable to x for what we're doing right now, because that'll be better. So it looks like 1 minus x times A plus x times B. And then this takes you from A to B as x goes from 0 to 1. So when x is equal to 0, this term drops out, and you just have A. When x is equal to 1, this part drops out, killing the A, and you just have B, right? So that's the idea. Okay, so then what we'll do is we'll take our new state variable w to be u minus, and then we'll take this linear combination. It's actually it's called a convex combination, because these coefficients 1 minus x and x, those coefficients add up to 1. So that means you get a point between A and B as long as x is between 0 and 1. So it's called a convex combination, and they come up in probability and geometry a fair bit. So let's see. Now we are on the interval from 0 to L, so I have to modify the parameter a little bit. So it'll be 1 minus x over L times alpha t plus x over L times beta t. And then as x goes from 0 to L, that'll take us from alpha to beta. Okay, so with this new variable, we can check to see the equation that it will be the solution of. It'll be the solution of LW equals minus, and then we'll have 1 minus x over L alpha plus x over L beta. Because when we feed W into the PDE, this part just dies, and we're left with minus the rest of it, right? So that's the trade-off. We get a non-homogeneity in the PDE, but now we have homogeneous boundary conditions. So W at 0 and at L will be equal to 0. Because when we, again, just by linearity, when we feed this in, the U will give us, at A, the U will give us an alpha, and then this will promptly subtract it back off again. Sorry, I said at A. I meant when we evaluate it at 0. And then we have to pick up the slack and check to see, okay, so what got stuck in the initial conditions. And so if you evaluate W at t equals 0, then you're going to be looking at, well, whatever you got from the U portion, and then also whatever you got from the other part. So this will be 1 minus x over L alpha 0 plus x over L beta 0. All right. And maybe I'll stick with those square brackets just because it apparently it makes me happy. Okay, and so, but the key point is that now, right here, we have homogenized the boundary conditions. And so then that means we'll apply we'll be able to apply some other solution technique. So let's look at some particular example. So if we take another heat equation example, so ut minus 3uxx equals 0, and we'll do this on the interval from x going from 0 to 1, t positive. And we'll take our boundary conditions to be 2e to the minus t on the left-hand side and 1 on the right-hand side. And we'll take an initial condition of x squared. Okay, so then I'm going to let w be u minus, and then I've got my 1 minus x 2e to the minus t on the left-hand side plus x times 1 on the right-hand side. And so when I substitute this in, I have the equation, or the new problem, wt minus 3 wxx is going to be 1 minus x 2e to the minus t. That's actually the time derivative of alpha, right, which kicks out a minus sign, so that cancels this minus sign here. And then I guess it's also worth noting that right here, that's where the b prime or the beta prime term would come. Oh shoot, where'd it go? Oh, it's up off the top of the screen. Okay, but that's where the beta prime term would go. But in this case, beta prime is going to be 0 because it does not depend on t. Then we have let's see. So now we've got w0t equals wlt equals 0, and we have w of x0 being, so there's the x squared from the original phi term, and then coming from substituting the rest of this business at t equals 0, we end up with plus x minus 2. And I should point out that this is in the book, this is missing. So I forget which example this is, but you'll find it in this section. And then the upshot or the key point here is that we've managed to homogenize, as I mentioned before. And so now this problem can now be solved by eigenfunction expansion. Or like we talked about just previously, you can split it into two parts and apply Duhamel's principle, etc. Oh, by the way, the book covers this material in sort of a weird order. When you read it, I would recommend you read 428, like, what is that, example 428, and then remark 430, and then remark 432, because they're all about this moving the boundary conditions technique.